All right. Last time we studied section 5, independence, basis, and dimension. We have already introduced the definition of linear independence, and we can check whether a series of vectors are they linearly independent or not. And also the basis defines as the sequence of vectors that could span the corresponding space. Now let's check the basis that could span a space. So two vectors cannot span all of R3 because two vectors are not enough, even if they are independent. So two independent vectors are not enough to span R3. But four vectors in R3, they must be dependent. That all depends on the dimensions of this R3. So that means we want enough number of independent vectors to span the space. That is called the basis. A basis for a vector space is the sequence of vectors with two properties. The basis vectors are linearly independent, and they can span the space. So, for example, there are two independent vectors, 1, 0, 0, and 0, 0, 1. They are two independent vectors, right? They are two independent vectors from R3, but they cannot span the full three-dimensional space. Try to take note. The full R3. Because two independent vectors are not enough. And in R3, any four vectors or any n vectors which n is greater than 3, n vectors, they are dependent. They are dependent to each other. So that is the definition for the basis. Okay? And we discussed this example 6 last time. The two columns from I2, they are independent, right? They are independent columns, and they produces the standard basis. Standard basis means they are unit vectors. Their length, the vector length, is 1. So other basis for this example, other basis for R2, 2, 0, and 0, 3. Those two are also independent vectors, and those two vectors are enough to span for R2, but they are not called standard basis. They are basis of R2. Are you clear? Because their lengths are not 1. They are not unit vectors, so they're not called standard basis. Now let's check more about the basis. There is one and only one way to write V as a combination of the basis vectors. If V1, V2 until Vn are basis vector, Be careful here, we didn't call a standard basis, okay? Standard basis is special one, which means each vector has the length 1. Are basis vectors for Rn. Then any vector v which is from Rn can be represented by the linear combination of those basis vector. And there is only one way. There is only one way to express this vector. And of course, the sequence of those n vectors are bases, so they can represent any vector because they can span the full Rn. So any vector from Rn can be expressed by the linear combination of those basis vector. And furthermore, there is only one way to express the vector v. So here, vector v is anyone from the Rn. Then there is one and only one way to write v as the combination of the basis vector. Now let's check the reason. If it's not, if v can be expressed as a1v1 plus a2v2 plus anvm, and also we can the vector v can be expressed as b1v1 plus b2v2 plus bnvm. Then by the subtraction, we will get 0 vector v minus v, and the right side will be a1 minus b1 times v1 plus a2 minus b2 times v2 plus an minus bn vm. So we know those bases, they are independent, right? They are independent vectors. So when z equal to 0, then all the coefficient ai minus bi should be 0, since the basis vectors are independent to each other, right? From the independence of all those vi's vector. So ai minus bi equals 0 for all the I from 1 to n. Then that means ai equals bi. There is only one way to express the vector using the linear combination of the basis vector. There are not two ways to produce v. Are you clear? So we give this statement and explain and somehow simply prove it. So do you have any questions so far? And be careful here. We said it's basis vectors. We didn't emphasize it standard basis. Now let's look at this example to discuss the basis. Okay, to discuss the basis for vector space. Here are two matrices A and B. A is invertible, but B is not. Now let's check how the basis can span the how the basis can span the space. Now for matrix A, we can perform the elimination and to check those columns are all pivot columns. Let's get the RRE form for matrix A. First row is the pivot row. Row 2 minus row 1, so we get 0, 1, 0, 0, 1, 1. 0, 1, 0. Second row is the pivot row. row 3 minus row 2. So we get 0, 0, 1. So that is I3, right? That is I3. Of course, those 3 columns are independent columns, right? This is the RRE form for A. And how can we find the inverse of A? You can start by A I3 as an augmented matrix, and after the eliminations, you can reach I3 on the left, then the right part gives the A inverse, right? So here, we know that in the RRE form, 3 columns are independent, right? So 3 columns in RRE form of this matrix A are independent columns. They are those 1, 1, 0, 0, 0, 1, 0. They are standard bases, right? Because their length is 1. The length for each vector is 1, right? They are standard bases for R3, right? They are standard bases for R3. They are independent columns, and they can span the full R3, and they are standard bases, right? They are standard bases. So since the 3 columns in RRE form are independent, how about those 3 columns in matrix A? 1, 1, 1. How about those 3 columns in matrix A? 0, 1, 1, 0, 0, 1. Those 3 columns in A are also independent, right? It's the same. Those 3 columns in A are also independent, and they are bases. They are not standard bases. They are bases for R3. Are you clear? So those 3 columns in matrix A, they are independent columns. And of course, those 3 columns can also span the full R3, but they are not standard one. The length of those 3 vectors are not 1. So they are bases for R3. Now, are you clear about the standard basis and the basis? And of course, for this matrix, the rank is 3, right? The rank for the matrix A is 3. So matrix A is non-singular and it's invertible, right? So that is the conclusion, okay? That is conclusion. Now let's look at the matrix B. And you will notice that second row and the third row, they are exactly the same. So we will have 0 rows, right? We will have 0 rows. So matrix B inverse does not exist. The matrix is called singular. 1, 0, 1. Row 2 minus row 1. 0, 1, 1. Row 3 minus row 1. 0, 1, 1. Row 2 becomes the pivot row. So row 3 minus row 2 will get 0 rows. And by the way, is it RRE form? Is it RRE form? So 0 rows occurs then B inverse not exist, right? B inverse not exist. What is the rank? What is the rank for B? And by the way, is this one RRE form for the matrix B? This one is the RRE form for matrix B, right? And there are two independent columns. The first two columns are independent. And the third column can be expressed by so number 2, there are two independent columns. One 0 0 and 0 1 0 are independent columns. And the third column can be expressed by the first two independent columns. That will be the sum of those two columns, right? Now, let me ask the question, okay? Now, let me ask the question. So, are those two columns 1 0 0, 1 0 0, and 0 1 0 basis for R3? Are those two independent vectors are basis for R3? Yes or no? Are those two independent columns 1 0 0, 0 1 0 called the basis vector for R3? Yes or no? So some students answered yes. So how many independent vectors are here? So a lot of students answered yes, right? How many independent vectors here? 3? How many independent vectors in matrix B? So what is basis? What is the basis vectors we said? First, those vectors, the sequence of the vectors should be independent to each other. Yes, it satisfies this condition, but can they span for R3? Are those two independent vectors 1 0 0, 0 1 0 can span for R3? The answer is no, right? The answer is no. This is the statement again. Two vectors cannot span R3. Two vectors cannot span R3. Two independent vectors cannot span R3, so they are not called bases. Are you clear? And since the first two columns in the RRE form are independent, so it's the same for the matrix B. Okay, for the matrix B. So here, how can we describe this one? I couldn't find any space to write it. So those two columns are independent. 1, 1, 1 and 0, 1, 1. Those first two columns in B are independent. They are basis for column space of B. Be careful of those statements. They are basis for the column space of B. And let me ask, what is the dimension of the column space of B? What is the dimension of the column space of matrix B? What is the rank for matrix B? It should be 2, right? Should be 2. The column space of matrix B is the subspace of R3. So for the column space, we only need 2 independent vectors. And those 2 independent vectors, they can span the column space. They cannot span R3. Are you clear? We will check those statements further, okay? So don't be confused. Those 2 vectors, those 2 columns in B, the first and second columns in B are independent columns. They are the same as 1, 0, 0, 0, 1, 0. They cannot span the full R3, but they can span the column space of matrix B. So they are the basis for the column space of B. And we know that the dimension of the column space for matrix B is 2. By the way, what is the dimension for the column space of matrix A? How about A? What is the dimension for the column space of matrix A? It's 3, right? It depends on the rank, actually. It depends on the rank. If the rank is R, then the dimension of the column space of the corresponding matrix, that will be R. Are you clear? All right, let's continue. Have you finished the note? Have you finished the note for this page? Yeah, please let me know whether you finished the note or not. It shows 60 or 58 students joined the Tencent meetings. It's good. So let me write one more comment here. Continue. The two columns from matrix B 1 1 1 0 1 1 are independent columns. They are bases for the column space of B, and the column space of matrix B is a subspace of R2. R3, sorry, is the subspace of R3. The dimension of the column space of matrix B is 2, but it's also a space in R3. Are you clear? It's also a subspace in R3. It might be a plane passing through the origin in R3. Are you clear? That is, now let's check the infinitely many different bases. The vectors v1, v2, vn are bases for Rn exactly when they are the columns of an n by n invertible matrix, which means for an n by n invertible matrix, every columns, all the n columns gives a basis for Rn. So in that way, there are infinitely many different bases. Now let's check the this matrix A. That is one matrix we find its inverse from the homework. Now for this matrix, we can reach the upper triangular form 0, 1, 3 or 1/3. Zero, zero, one. The last row is 0, 0, 1. And if you perform the elimination again, then you can reach that. The RRE form for matrix A is I3. This is the RRE form of matrix A. Sometimes we call the matrix R, right? Sometimes we call it, the textbook call it matrix R. So here, matrix A and its RRE form, they are equivalent. They are equivalent. So for the RRE form, it's very clear. 3 columns are independent, right? 3 columns are independent. And those 3 vectors, column vectors, those 3 vectors are standard basis for R3. What is the rank? What is the rank for this matrix A? And what is the dimensions for the column space of A? Should be 3, right? Should be 3. And let's check for the matrix A. For matrix A, those 3 columns are also independent according to its RRE form. Those 3 columns are independent, and their bases, they are not the standard one, but their basis for R3. 3 independent vectors can span the full R3. Now let's go back. What is the rank for A and what is the dimension for the column space? So the rank is 3, right? Because in the RRE form, there are 3 pivot columns, independent columns. What is the dimension of the column space for the matrix A? It's also 3, right? So here, those 3 columns are independent and they are basis for R3. This A inverse exists, right? For this matrix A inverse exists. So those 3 columns are basis for R3. And if we go back, these 3 columns in matrix A, 1, 1, 1, 0, 1, 1. Now let me continue here. So another matrix in the previous slide, this is another matrix A, 1, 1, 1, 0, 1, 1, 0, 0, 1. So this is also 3 by 3 matrix. A inverse exists. A inverse exists, which means the rank is 3. 3 columns are independent. So those 3 columns in this matrix A are also a basis. Those 3 vectors are also a basis for R3. Those 3 columns are independent. And they are basis for R3. Are you clear? That is what does this statement mean. They are basis for R3. So for any given 3 by 3 matrix with the inverse exist, those 3 columns are independent and they are called the basis for R3. So there are infinitely many different bases. Are you clear? And it's true for any n. It's true for any n-dimensional space Rn. That is what does this statement mean. The vectors v1, v2 until vn are basis for Rn exactly when they are the columns of an n by n invertible matrix. If they are the columns of an n by n invertible matrix, which means those n columns are independent. And they can span the full Rn. So they are called the basis for Rn. And only for the R3, only those 1, 0, 0, 0, 1, 0, 0, 0, 1 are called standard basis. Only one standard basis. Those are standard basis, but those are not standard one, but they are still called the basis. Are you clear? Now it's almost time. Let's take a 5 minutes break, then we will continue. All right, let's continue. A basis for vector space. The pivot columns of A are basis for its column space. The pivot rows of A are a basis for its row space. So are the pivot rows of its echelon form R. So be careful. Here we said the pivot columns of A are a basis for its column space. They are not full space of any Rn. Now let's review this example again. This given matrix A and its RRE form is this one. So the rank First, the rank of the matrix A is 2, right? Is 2 because there are 2 independent columns, right? There are 2 independent columns. 2 independent columns. 1 0 0 and 0 1 0, right? Those 2 independent columns, and we have already known that 2 independent columns, they are not the basis for R3, right? They cannot span the full R3. 2 independent columns. They are not the basis for R3, but they are basis for the column space of A. And what is the dimension of the column space of A? What is the dimension? What is the dimension of the column space of A? Should be 2, right? Should be 2. And since the first 2 columns in matrix R are independent, then the first 2 columns in matrix A, 1 2 1 and 0 1 0, 0 1 0, 1 2 1, 0 1 0, they are also independent, right? Are independent columns. And they are basis for the column space of A also. And we know there are different bases. They are also the basis for the column space of A. And what is the dimension? Dimension of the column space of matrix A is 2 because the rank, right? It's the same as the rank of the matrix A. Now, did you understand those statements? For this given 3 by 3, this given 3 by 3 matrix, this rank is 2, so A is singular. That is one example we did before, right? For the square n by n matrix, when the matrix is singular, then the columns the columns are basis for its column space. They are not basis for the full space Rn. They are not space for R3, but they are basis, and especially 1 0 0 0 1 0, they are standard basis, right? They are called standard basis for column space of A. And we know the dimension of the column space of matrix A is 2. So that is what we said here. The pivot columns of A are basis for its column space. So be careful, for its column space. And it's the same for the rows. Okay, pivot rows gives the basis for its row space. And it's the same on its echelon form R, right? So like those first 2 columns, they are basis. They are independent columns. They are basis for the column space of A. So it's the same for the first 2 columns in A. They are equivalent. Any questions so far? So trying to understand this statement. The pivot columns of a matrix A are a basis for its column space, but especially if matrix A is n by n invertible, if matrix A is n by n invertible, so which means n columns are independent, right? N columns for the matrix A are independent. Then in this way, the n columns, which are all pivot columns, right? The pivot columns, because the n columns are all pivot columns. Those pivot columns are a basis for Rn. Especially when A is invertible, the dimension of the column space of A is n because the rank is n. It's invertible. Are you clear? So this is the special case. When the matrix A is invertible, the rank is n. Then the dimension of the column space of A is n. Then in this way, those n columns are pivot columns. Those n pivot columns are a basis for Rn. But if the matrix is not, the inverse does not exist, here the rank is less than 3, right? Here this rank is less than 3, so the dimension is also equals the rank 2. In this way, they are basis for its column space, not the full R3. Are you clear about the difference? And that is what we discussed before for matrices A and B, right? Have you finished the note? Now let's check one more example when the matrix A is 3 by 4. 3 by 4. 3 rows, 4 columns. Now we can reach its upper triangle form, and this is the RRE form. So for this one, this is also one matrix we discussed before. What is the rank? What is the rank for this matrix A from its RRE form? It's 2, right? It's 2. And in a matrix R, the first 2 columns, 1, 0, 0, and 0, 1, 0, are independent columns, right? Are independent columns. Of course, they are not basis for any R3 or R4. It's not, because it's only 2 independent vectors, right? Only 2 independent vectors. They are not, those 2 independent. Here I said columns of vectors. They all means column vectors. Okay, they all means column vectors. So those 2 independent columns cannot span R3. Nor R4. Those 2, they can only span the column space for the matrix A, right? Those 2 independent columns, they can only span the their basis for the column space of matrix A. Here is the matrix A. They are basis for column space of matrix A, and column space of matrix A is the subspace. Is the subspace of R3 or R4? Of R3 or R4? Here. That means what is the dimension? Sorry, it's not about the dimension. So the column space of matrix A is the subspace of R3 or R4. Check what is the dimension for the vectors in column space. Those two are vectors in the column space. 1, 0, 0, 0, 1, 0. What are the components? How many components do they have? 1, 0, 0, 0, 1, 0. They are columns. They are vectors from the column space of A. So they are the vectors in R3. So column space of A is the subspace for R3, not R4. Are you clear? So don't be confused, okay? Don't be confused because here A is a rectangular one. It's 3 by 4. Then the dimension of the column space is 2 equals to the rank. But the column space is the subspace of R3. Are you clear? Here we give one more example. The matrix A is a rectangular one. Any questions so far? Of course, those two independent columns, they cannot span R3 or R4, right? And comment number 3, since the first two columns in matrix R are independent columns, so the first two columns in matrix A, 1, 1, 1, 1, 2, 3 are independent columns, right? They are independent columns, and they are also the basis for the column space of A, right? They are also the basis for the column space of A. So please let me know when you finish the note. Have you finished all the note? All right, let's continue. So that is all for this section. Okay, let's review the key ideas. We spend 3 classes on this section to discuss the independence, basis, and the dimensions. The columns of A are independent if x equals 0 is the only solution to Ax equals 0. That is one definition for linearly independent, right? Linearly independent. If 0 vector is the trivial solution to Ax equals 0, then all the columns in A of A are pivot columns. All the columns are linearly independent. The vectors v1, v2 until vr span a space if their combinations fill that space. So be careful. Here we didn't say they fill the full space Rn, right? Those vectors span a space if their linear combination can fill that space. That space might be a subspace. which means every vectors from the space can be represented by the linear combination of all those R vectors. A basis consists of linearly independent vectors that span the space. So that is the two properties for the basis. The basis for a vector space, right? There are two properties for the basis. The basis should have enough linearly independent vectors. Enough implies they can span the whole space. And every vector in the space is a unique combination of the basis vector. We explain the reason, right? There is only unique way to express the vector. All bases of a space have the same number of vectors. Here, this basis, which means one group of bases, another group of bases. So those are two different bases, like the examples I gave before. For two different 3x3 matrices, 3 columns in one matrix A that form a basis for R3, and another 3 columns in an invertible matrix B, they can also form a basis for R3. So those are two groups of bases, but the number of the vectors are all 3, right? 3 independent vectors will span the for R3. That means they will have the same number of vectors. This number of vectors in the basis is the dimension of the space, of course, right? That is why we said the column space, like the previous example, the matrix A is rectangular, the matrix A is in 3x4, but the rank is 2. So only 2 independent vectors can span the column space of matrix A. We only need 2 independent vectors. They can span the column space of matrix A, and we know the dimension of the column space of matrix A is 2. That equals the rank R. Number 5, the pivot columns are one basis for the column space. We know that, right? No matter they are in matrix A and in matrix R, they are all bases, right? They are two different base for the column space, and we know the dimension is R, right? The dimension of the column space equals the rank R. So that is for section 5. Okay, that is for section 5. Try to review all the notes and understand the examples. Now let's start the last section of this chapter, dimensions of the 4 subspaces. Actually, we have already studied some of those subspaces. Now let's check. Okay, let's check. The main theory in this chapter connect rank and dimension. The rank of a matrix is the number of pivots. The dimension of a subspace is the number of vectors in the basis. We count pivotals or we count basis vectors. The rank of A is very important. Okay, the rank of A, this number R, reveals the dimensions of all 4 fundamental subspaces. Now let's look at those 4 fundamental subspaces. The row space of matrix A, that is the same as the column space of A transpose, right? Because the rows in matrix A are the columns in its transpose. So we look at the column space for A transpose. And the second subspace is the column space for matrix A. That is what we discussed a lot in section 5. The null space is NA. We also discussed this one before. Number 4, the left null space for A transpose. So this is a new one. Okay, we will try to understand this new one. So those are 4 subspace, and we will check why there are some of them are subspace of Rn, why there are some of them are subspace of Rm. So here the A is the general size in M by N. Okay, A is the matrix in M by N format. We will check it later. Okay, don't be confused. Okay, don't be confused. So here, matrix A is in M by N format, which means M rows and N columns, right? M rows and N columns. Now let's check the second one first. Think about the second one. Second one, the column space of matrix A. So think about the column in matrix A. Each columns in A have how many components? N or M? Think about it. The matrix A is in M by N format. Now when we considering the column space, so the columns from matrix A has how many components? Should have M component. Right? M, it's not N, it's M component. Each column in matrix A has M component. So they are vectors from Rm. They are vectors from Rm. That's why we said the independent or the pivotal columns in matrix A form the column space of matrix A, and this column space is the subspace of Rm because the vectors, the column vectors, has M component. They are the vectors from Rm. So in similar way, you can check the row space. You can check the row space for matrix A. Think about each row in A. Think about each row in matrix A has how many components? Each row in matrix A has how many components? Should has N component, and they are vectors from Rn. The pivotal rows in matrix A, they can span the row space for matrix A, which is the same as the column space of A transpose. So they are subspace of Rn. That is what we said. They are a subspace of Rn. Now this one, the null space is the subspace of Rn. Are you clear? Because the solution to Ax equals 0. The solution X should be the vector from Rn, right? Should be the vectors from Rn. So the null space consists of the solutions to the linear system Ax equals 0. That is the subspace of Rn. And in a similar way, you can think about the null space of A transpose. That means the solution to the Ax equals 0. In this linear system, the x should be the vectors from Rm. That's why this left null space is the subspace of Rm. So even though we only have two numbers, m and n, to describe the format of matrix A, right? M and n, m rows and columns. But don't be confused of the subspace. Row space and the null space, they are subspace of Rm. Column space is the subspace of Rm. So is the left null space. Are you clear? Now let's use one example. Let's use one example to check those four subspaces. So for this example, this is the matrix, and this is the RRE form actually for 3 by 5 matrix. M equals 3, N equals 5. R, the rank is 2, it's obvious, right? There are two pivot columns. So the rank is 2. Now let's check the column space first, right? The rank of this matrix is 2. No problem. Now let's think about the column space first. We are more familiar with the column space. Column space of A, we can also consider the columns in this RRE form, right? In this RRE form, there is no problem. So those two columns are independent. 1, 0, 0 and 0, 1, 0 are independent columns, right? Those two are independent columns. They are the basis. They are the basis for its column space, right? They are the basis for its column space. Number 2, what is the dimension of this column space? What is the dimension of this column space? Should equals to the rank R, right? Should equals to the rank R. And the column space is the subspace of R3 or R5. The column space is the subspace of R3 or R5. Think about the columns. The columns 1, 0, 0, 0, 1, 0, they are vectors. How many components do they have? 3 components, right? So they are the subspace of R3. Are you clear? So that is what we said. The column space is the subspace of Rm. These 3 is Rm. Are you clear? So that is the column space. Have you finished the note? Now let's read the comment for the column space. So the pivot columns 1 and 4 form a basis for column space of R. Column space of R is the same as the column space of A, right? No problem. They are independent columns because they start with the R by R identity matrix, which means those two columns, we can get 1, 0, 0, 1 from those two columns. So no combination of those pivot column can give the 0 column, which means they are independent. We cannot use one of them to express another. And they also span the column space, which means any vector from the column space can be expressed by the linear combination of those two pivot columns. And it's obvious the column 2 and column 3 are free columns. Column 2 is 3 times column 1. Column 3 is 5 times column 1. And column 5 is the linear combination of two pivot columns, right? So free columns are dependent, right? We can use the linear combination of pivot columns or independent columns to express the other 3 free columns, right? So that is about the column space. We will discuss the null space after the row space, okay? After the row space. Now, let's check the row space, okay? Let's check the row space. Of course, we can check that 3 rows, there is 1, 0 rows. So 2 pivotal rows, right? 2 pivotal rows. So the rank for the row space is also 2. And if you are not so clear, we can check the transpose. Okay, we can check the row space of this R is the same as the column space of its transpose. Now let's check its transpose. 1 0 0 3 0 0. Get the transpose of this R. 0 1 0 7 2 0. Of course, this is not RRE form. We need to get the RE form for this R transpose. First row is the pivotal row, so we can get 2 0 rows. 0 1 0, and this is 7 2 0 2 0, and with the fourth row we can get the last row is also 0. So we can get the RRE form, for the R transpose. The last row also 0 rows. So this is the RRE form for the R transpose. We need to discuss the columns in R transpose. So it's obvious, right? 2 pivotal columns, 2 independent columns. 2 independent columns in R transpose, right? Why we need the column space for R transpose, that are the row space, the rows for the matrix R. That is the row space for matrix R. So first, the rank of the row space, which is the rank of R transpose. The rank of R and the rank of R transpose, they are the same. So the dimension of the column space of R transpose, which is the dimension of the row space of R, that is 2. So number 3, 2 independent columns. 2 independent columns. 1 0 0 0 0 0 0 0 1 0. 2 independent columns. They are bases for column space of R transpose. They are also the basis for row space of R, right? They are also basis for the row space of R. The row space of R and the column space of R transpose, they are equivalent. And one more comment. The column space of R transpose is the subspace of R3 or R5. The row space of R, is it a subspace of R3 or R5? Check the 2 independent columns. They are vectors from R5, right? 2 independent columns, they are vectors. They have 5 components. So column space of R transpose is the subspace of R5. Are you clear? So that's what we said. The row space of matrix A is the subspace of Rn. right? Is the subspace of Rn. Also, you can look at this by the rows, but I think it will be much more clear to look at it by the transpose of R, right? Transpose of R to get the RRE form of the transpose matrix. So that is the second subspace we discussed. Now let's check the null space a little quick. Null space. This is the matrix R, right? This is the matrix R in the RE form. So what is F? The two pivot columns gives the I2, right? I2. So what is the matrix F? That will be 3, 0, 5, 0, 7, 2, right? That is the matrix F. Now, let's fill up the matrix N, the null space. This is a review for the section 2 and 3. The null space matrix N is, be careful when we fill up the N, okay? Here, x1 and x4 are pivot columns. So the first and the fourth columns are pivot columns. So x1 and x4 are pivotal variables. So x2, x3, x5 are free variables, right? Free variables. How can we find the spatial solution? How can we fill up the matrix N? We need to set up the 0 and 1s for free variable. Here we are discussing the linear system Rx equals 0. Okay, Rx equals 0. So the technique is to set up free variables as 0 and 1s. So we will set up as for x2, x3, x5, 1, 0, 0, 0, 1, 0, 0, 0, 1. How can we fill up this minus f? We are going to fill up those two rows for x1 and x3. So we get minus 3, minus 5, minus 7, 0, 0, minus 2. So there are three spatial solutions. They call it S2, S3, S5. It doesn't matter. There are three free variables in this matrix. Of course, there are three spatial solutions, and Rx equals 0 has a complete solution. You can express using x2, x3, x5. They are real numbers, or as usual, we can express the solution as C2S2 plus C3S3 plus C5S5. It doesn't matter. You write C1S1 plus C2S2 plus CS3S3. It doesn't matter. The textbook, they just write S2, S3, S5. We just follow that. It doesn't matter. You write S1, S2, S3. They denote those three spatial solutions. It doesn't matter. So this is the spatial solution, right? This is the matrix M. So there is the spatial solution for each free variable with n variables and r pivotal variable. Then the other n minus r will be free variables, right? So what is the dimension? What is the dimension for the null space of R? The dimension for the null space of R, that depends on the number of spatial solutions. We have three spatial solutions, right? We have three spatial solutions. So the dimension of this null space is 3. So this is number 1. Number 2, those three vectors, minus 3, 1, 0, 0, 0. Of course, those three spatial solutions, they are independent, right? They are independent. That's why we set up the free variables as 0 and 1s. They are independent. So those three vectors or those three columns are independent columns, independent vectors. They are the basis. They are the basis for the null space, right? Those three spatial solutions are called, they are the basis for the null space of the matrix R. And one more, number three, this null space is a subspace for R3 or R5. Is it a subspace of R3 or R5? R3, the null space of the matrix R, is it a subspace of R3 or R5? Should be R5, right? It's the subspace of R5 because each vectors, each columns in null space, they have 5 components. So that's why we said the null space is the subspace of Rn. This 5, that implies the n, the number of columns. So for this section, there is only one left, the null space of R transpose. Okay, the null space of R transpose. You can check this one by yourself. Okay, get the R transpose and try to solve the left null space. So for the left null space, the left subspace, we need to consider the spatial solutions to R transpose X, and the null space of R transpose is the subspace of Rm, which is the subspace of R3. You can read this, the last subspace by yourself, okay? So we will stop here today, and we will still meet next Monday, okay? Next Monday, but don't forget the homework 3 is due this Sunday evening, and homework's chapter 3 note will be due next Tuesday. So we are done, okay? We are done for chapter 3. Try to take all those notes for chapter 3 and upload to the Rain Classroom. So we will meet next Monday, 2:30. If the Rain Classroom doesn't work again, we still need to use the Tencent meetings. And so we stop here, but